Hello guys, this is CodeNCode and this is video editorial for the problem Kirei Attacks the Estate. Hopefully I'm pronouncing the name correct, right? This is an E problem from Div 3 contest, right? So the problem based on graph and we'll solve the problem using DP on tree, right? So let's have a look at the problem statement first. So the problem statement says that you are given a tree with n nodes and n minus 1 edges. Of course, it's a tree, so it will have exactly n minus 1 edges for n nodes, right? And node 1 is the root of the tree. This is specified in the problem statement. Now what you have to do, you have to calculate the threat value of each node. So the threat value of each node is calculated something like this. For example, this is the tree, and it has 5 nodes, right? One is connected to 2, one is connected to 5, 2 is connected to 3, 3 is connected to 4. This is the tree, right? And each node has a certain value. For example, 1 has 4, then 5 is 7, value of 2 is 5, 3 is 2, and 6 is 4. So these are the values in red, right? Now we are assessing the threat value of each node, right? Let's take an example of node 4. When you're assessing the threat value of node 4, what you will do, you will take all of the prefix from that node to the root, right? So it will be either 4 or 4 3 or 4 3 2 or 4 3 2 1, right? So here you see 4 4 3 4 3 2 4 3 2 1, all of the prefix from that node to the root, right? And then you will, what you will do, you will take their values and you will add and subtract alternatively. So value of 4 is 6, so it is 6. Value of 4 and 3 will be 6 minus 2, because value of node 3 is 2, and since it is going to be positive negative alternatively, so it will be 6 minus 2, so 6 minus 2. Then the next prefix is 432, which is 6 minus 2 plus 5, right? So 6 minus 2 plus 5, 1 plus, then negative, then plus, then negative, so on and so forth, starting from that node, right? So either it will be 6 or 6 minus 2 or 6 minus 2 plus 5 or 6 minus 2 plus 5 minus 4, right? 6 minus 2 plus 5 minus 4. So starting from that node, you can take any prefix, and whenever you will take the prefix, you'll have to add the values, add or subtract alternatively, starting from the positive value, right? And out of all of this, out of all of the possible prefixes, right, you have to take the maximum value. So if you see, if you take only 4, it is 6, 4 3 is 4, 4 3 2 is 9, 4 3 2 1 is 5. Clearly 9 is the maximum value, so that will be the threat value of node 4, right? So for each node you have to calculate its threat value. That is the problem statement, right? And the number of nodes are 2 into 10 to the power 5, and value of each node can be as max as 10 to the power 9, right? So yeah, this is the problem statement. This we have to solve in linear time, max and log n, right? Because n is 2 into 10 to the power 5. So let's see how we'll solve this problem, right? All right, so let's make some observations. So first of all, when you're calculating threat value of node 6 in this tree, it's kind of a bamboo tree, right? One is connected 2, 3, 4, 5, 6, things like that, right? On the right hand side, you can see their values, right? Now, when you're calculating threat value of node 6, what you will do, you will have to calculate the prefix sum, maximum prefix sum, either be 4 or 4 minus 2, right? 4 minus 2 or 4 minus 2 plus 3, 4 minus 2 plus 3 minus 7, right? Things like that. So these are all of the prefixes for node 6 in this tree. Now what we are actually looking for in this, if you could see, we are looking for the maximum prefix sum. If we see, all of this is nothing but prefix of 4 minus 2, 3 minus 7, 5 minus 4. This, all of these are actually prefixes of this. So what you are looking for a particular node is the prefix sum from that node to the root, right? Prefix sum from node to the root, that is exactly what we are looking for, maximum prefix sum, right? Now the same you can say that you are looking for the maximum suffix sum from root to the node. From node to root, it's a maximum prefix sum, right? Maximum prefix of this 4 minus 2, 3 minus 7, 5 minus 4. This is from left to right. If you look at it in terms of node to root, it is maximum prefix sum. But if you look at the other way, what you're basically calculating is maximum suffix sum from root to the node. Why I am fixating on from root to the node? Because there are so many other nodes if you look at it in this way, that you have to go from node to root, there are so many nodes, and you have to go from those nodes to the root, right? In many cases you may have to run multiple DFSs. We can't do that, but from root we can reach every single node in single DFS, right? So it's better to look it in a way that from root to every single node, right? So from root to every single node, what you are looking for is a maximum suffix sum on path from root to that node, right? All of this is nothing but the suffix of 4 minus 2, 3 minus 7, 5 minus 4, which is path from root to the node, right? So what we are looking for is a maximum suffix sum on the path from root to certain node, right? So this is what we are looking for, right? All right, so let's have a look at observation 2 and 3, right? So now we have a bamboo tree again, and what we are going to do, we are going to calculate the thread value of node 4 and 6. For node 4, it would be 4, 3, 2, 1. This is the path 4, 3, 2, 1 from node to root, and that would be 3 minus 7, 5 minus 4. 3 minus 7, 5 minus 4. Now for node 6, it would be 6, 5, 4, 3, 2, 1, which is this path, and the node values it would have is 4 minus 2, 3 minus 7, 5 minus 4. That's exactly what we are having here. If you see, for both of these nodes, certain part of the path and also of the value array is common, right? Using this, you can understand observation 2 and 3. So observation 2 says that all of the nodes on the same path from the root, right? As you can see, 4 and 6 are on the same path from the root, right? Now all of the nodes on the same path from the root have same prefix value in the array, if you can see, right? I'm calling it prefix because you would read it from right to left from root, right? We'll fixate ourselves on the root to the node. So this is called, I'm calling this prefix because 4, 5, 7, 3, 4, 5, 7, 3 are from root towards node. That is why they have the same prefix, right? So observation 2 says that all of the node on the same path from root will have same prefix, right? That is observation 2, right? And this is important because, as you can see, if they have the common part, when you have already calculated result for node 4, you maybe utilize this result to calculate for node 6. You don't have to calculate this part again. This way you can save time, right? You only calculate for minus 2 and 4. You don't have to calculate for 3 minus 7, 5 minus 4 again, because you have already calculated it. So when you're moving from root to certain nodes one by one, you already have the result. All you have to do to build result, for example, when you are from 1 to 4, right? Already you have calculated result for 4. When you're going to calculate for 5, you can already see that 3, 7, 5 and 4 are prefix of the path of 5 to root also. So instead of again calculating 3, 7, 5 and 4, what you can do, you can utilize the result which you have calculated in previous DFS call. We'll use DFS, right? Till node 4, and utilize that result to build result for node 5, right? Because they have common prefix, and that is where observation 2 will help you, right? Very trivial observation, but important one, because this helps you save time. Now the other observation, the observation number 3, is that nodes on the same path that are also at same distance parity. Same distance parity means they are on the same level in terms of odd and even. So all of the nodes which are at the even distances from the root, for example, and also all of the nodes which are at the odd distances from the root, for example, 0, 1, 2, 3. Node 4 and node 6 are at distance 3 and 5, right? Root is at distance 0, right? So node 4 and 6 are at distance 3 and 5. So both of them are at odd distances. If that is the case, what we'll have the same signs in the value array. So this is the value array, right? And they will have the same sign, right? 3 minus 7, 5 minus 4, 3 minus 7, 5 minus 4, because both of them are at the odd distance. If you take a look at this, my bad, what is that? Just a second. I don't know how it's, okay, yeah. If you take a look at this, node 3 is at even distance, 0, 1, 2. Node 3 is at 2 distance, right? So this is at even distance. If you look at it, 7 is at positive here, while for node 4 and 6, which are at odd distance, 7 is negative, right? So you can't just utilize node 3's prefix to calculate result for node 4's prefix, right? You can't do that because they would have different signs. For node 4, 3 would be positive, 7 would be negative. For node 3, 7 would be positive, right? So all of the nodes which are at the same distance parity will have same sign, right? All of the nodes which are at odd distances will have same sign, same value sign, right? And all of the nodes which are at even distances will have same signs also, right? So somehow we have to take care of two different things: nodes which are at the odd distances, nodes which are at the even distances, right? So these are important three observations. Hope you understand. Hope you understood these. Once we have these observations, we can try to build the solution, right? And we are going to use Cadence algorithm. So let's say I wanted to calculate maximum suffix sum from root to node 5. How I'll do it, I'll start from root and we'll build my solution till node 5, because of course we'll start from root and we'll build solution for each node, right? That's why I'm taking this part, right? So I'll start from node root node, and it will be value of node 4, I'll take it positive, not negative, because for node 5, 2, 7 and 4 all will be positive, right? Right. So how we'll decide which one will be positive, negative, I'll explain in the next section. Here I only want to explain you that how we'll build the solution. So I'll start from root, which is having value 4, right? So this is my prefix. What is the maximum suffix sum I can have if my only array is 4? Maximum suffix sum I can have is 4 only, right? Simple. I'll move on to the next node, which is node 2, and its value will be -5, right? -5, because next node will be negative. Now if I have an array 4 minus 5, what is the maximum suffix sum I can achieve, right? Which is basically what is the maximum sum ending at this point. Whatever maximum sum ending at this point you want, you calculate it using Cadence algorithm. If you don't know Cadence algorithm, you can go ahead and learn that first, and then you will be able to understand it better. Otherwise, I'll explain it in a very simple way. The way you calculate it is what is the maximum sum ending at this point is simple. Value of this node plus bonus. Bonus is what I have till previous index. Till previous index I had 4, right? Maximum sum was 4 till previous index. If I add that, that is my bonus to my current value, which is -5. 4 minus 5 is -1. -1, you don't want that, right? In some portion that you solve using Cadence algorithm, you actually take that -1. But here we don't have to take that. I can simply ignore that. So I'll take it 0, right? I want maximum value that I can take. So either I can take -1, because bonus is 4 and current value is 5, -5. So 4 minus 5 is -1. Either I can take -1 or I don't take anything. We have that option. If I don't take anything, the result will be 0. So maximum suffix sum till if we have only 4 minus 5 is going to be 0, right? Now next element is 7. So again, what is the bonus till the last index? It is 0, right? From this sum array, I already know till last index maximum I was getting was 0, right? And if maximum I was getting till last index is 0, that means my bonus is 0, current value is 7, 0 plus 7 is 7, right? Next is -3. So bonus is 7, current value is -3. What will be the overall sum? 7 minus 3, that is 4, right? So if we have 4 minus 5, 7 minus 3, maximum suffix sum you can achieve for this is 4. You can try that, right? And this is Cadence algorithm. Now I'll get for 2. So bonus is 4, next value is 2, 4 plus 2 is 6. So if you look at this, if you have this array, the maximum suffix sum that you calculate ending at this is 6. And how we calculate it? Using Cadence algorithm. And so I can keep on going through the DFS calls. Each time when I reach a certain node, I'll just decide whether to add it or to subtract it, right? Based on the parity. If the first node is I'm adding, then the next node I'll subtract, right? Using the parity, I can decide that. And finally, when I'm at node 5, the maximum suffix sum is 6. You can try that. If you are at node 5, the maximum thread value will be 6 only. So how we are calculating it? Using Cadence algorithm, simple DFS. From root, we are going each node. At each level, we will decide whether to add it or to subtract it. Okay? And how do you decide that? I'll explain that in a moment. But you understand that you will utilize Cadence algorithm. All you have to do is keep a sum with you, and each time when you're reaching a certain node, you take its value, either add it or subtract it, right? And sum's value will never go below 0, right? Because we have the option to discard it. If I'm getting negative, I'll say I don't want it, right? I'll take 0, right? That's exactly what we are doing here. This is basic Cadence algorithm. Now, how do you decide whether to add a value of a certain node or to subtract it? So if you see here, the way I went through this example is that I took root's value as positive, then the next node negative, then the next node positive. So if you see, for this, all of the nodes which are at even indices, even distances, 0, 2 and 4 are positive. 0, 2 and 4. This is for node 5, but there are certain nodes for which so for this series, all of the nodes which are at even distances are positive, right? Because a node 5 for which we were calculating itself is at even distance. For example, 0, 1, 2, 3, 4, right? The node which is at even distance, for this node, all of the nodes which are at even distances will be positive, and all of the nodes which are at odd distances will be negative, right? As simple as that. Now, if you are calculating for node 4, which is at odd distance, what you will have, starting from if you were calculating for node 4, or let's say, or there was some other node here, any node which which is at odd distance, for example node 4, what you will do, 3 minus 7, 5 minus 4. So what you are doing here, in such scenario, for node which are at odd distances, when you are calculating for them, all of the nodes which are at the odd distances will be negative, right? All of the nodes which are at odd distances will be negative from that node, unfortunately. So all of the nodes which are at odd distances will be negative. But from root, again, node 4, again, node 1 is at 0 distance, but still we are taking it as negative for node when we are calculating thread value of node 4. So same nodes sometimes are taken positively, sometimes are taken negatively, right? And so for this reason, you have to maintain two different series. One you can call even series, in which all of the nodes which are at even distances, for example, node 1, node 3, node 5, you can take them as positive, and you can carry another series which you call as odd series for those nodes who are at odd distances from root. For example, for node 4, node 2, nodes like that, right? You can calculate an odd series, because for such kind of node, the signs will be flipped, right? 4 minus 5, 7 minus 3, 2. Here it is flipped, minus 4, 5, minus 7, 3, and minus 2. So you have to carry two different series, right? And this even series will help those nodes which are at even distances, and odd series will help those which are at odd distances. For example, for even series, for node 4, the result is actually 4. This is prefix sum, right? This is maximum suffix sum from root to certain node, right? So root node basically is at 0 distance. So this is its result. The maximum thread value of node 1 is actually 4. Now node 3. For node 3, I'm here. The maximum thread value is 7. For node 5, maximum thread value is 6, right? So all of these nodes are at even distances. So you will create two different series. One series, we call it even series, in which you starting from the root node, basically all of the nodes which are at even distances, you will keep them as positive, right? All of the nodes which are at odd distances, you will keep them as negative. As you are moving through, if a certain node is at odd distance, you will subtract from some, otherwise you will add it, right? And you will also maintain an odd series. Odd series will help the node which are at odd distances from the root. For example, node 4. Node 4 will have 3 minus 7, 5 minus 4. So you see 3 minus 7, 5 minus 4, right? So for all of the nodes which are at odd distances, odd series will help them. So for odd series, when I am at node 1, I'll actually subtract 4 from sum, right? So my first value will be minus 4. So if only I have minus 4, my prefix sum, suffix sum will be 0, because minus 4 I don't want to take it, 0. For next, I'll have 5 minus 4. If I have 5 minus 4, what I'll do, I'll take the bonus which is 0, add 5 to it, it becomes 5, right? So things like that. So we have nodes at odd distances, we have node at even distances. For calculating the result of odd distance, we'll calculate, we'll use the odd series, and calculating the result for even nodes, we'll use the even series. So we have to maintain two different series. This will become much more clear when I'll explain this using the dry run, right? So let's say this is our tree, and we have to calculate result for all of these nodes. We have 5 nodes, right? Value are 4, 5, 7, 2, and 3, right? This is the result array. I'll save the result here. I'll keep two different series, odd and even, and this is the level of the node we are processing currently, right? And then we have odd series, even series. This is just to show you. In DFS, I'll carry only these three things: level of the node, even series, and odd series sum, right? Prefix sum till that node. That will be basically your result, right? So let's start. So I'll start from root node, which is at distance 0, right? If I'm starting from 0, if you remember, in odd series, since node is at even distance, right? It is at 0 distance, even distance. From odd series, its value will be subtracted. From even series, its value will be added. Basically, for odd series, this will be negative, and for even series, this will be positive. Right? Simple. Now, for odd sum will be 0 and even sum will be 4. Why? So if I only have an array whose value is -4, what is the maximum suffix sum? 0. Yeah. If I have an array whose value is only 4, what is the maximum suffix value? 4. Right? Cutting the algorithm. Now we have calculated this 0 and 4. 0 is the odd sum series, and 4 is the even sum series. Now L is equals to 0. That means current node is at 0 distance from the root. That means at even distance. So even series will be the result of this. That is why in the result for node 1, I have saved 4, which is even series value. Right? If you try to calculate the thread value of node 1, that will be the thread value. From here, we'll make a DFS call to node 2. We are at node 2. Its value is 5. Right? Again, in the odd series, you will add it. Why? Because this is at odd distance. Since this is at odd distance, in odd series you will add it. In even series you will subtract it. Simple. Right? So if we add 5, right? If this is the prefix, if this is the array, maximum suffix sum you can get is 5. If you apply the cadence algorithm, it's simple. Till now, the bonus is 0. If you add 5 to it, it will become 5. Till now, bonus is 4. If you subtract 5 from it, it will become -1. We don't want -1, we'll make it 0. So it would become 5 and 0. Simple cadence, right? So all you are looking in the DFS is that what level you are. If you are on the odd level node, in the odd series you will add it. In the even series you will subtract it. If you are at even level node, in the even series you will add it. In the odd series you will subtract it. Right? That's how we have built even and odd. And since we are at odd distance, the current node's value will be the value of the odd series. That is 5. If we try to calculate the maximum thread value of node 2, it would come out 5. That would be 5 minus 4, right? 5 minus 4. Maximum suffix sum 5 minus 4 cadence algorithm, which we have been applying to get these two values. This is just to explain you. I'm only keeping two integer variables, right? And the value is 5 and 0. And this is odd, so I'll take the odd value, and that would be result of node 2, which is 5. Right? I'll go to the next node, which is at even distance. So 7 will be added in the even series, subtracted in the odd series, right? So 5 minus 7 is -2. I don't want -2. I'll make it 0, right? And then -5 plus 7 is sorry, even series is 0. 0 plus 7 is 7, so it would become 7, and that would become 0. As I am on the even level, even series value is my result, right? So for node 3, result will be 3. So, and I am also saving what is the odd and even here along with the node, because sometimes you have to roll it back. For example, from node 3 you are going to node 2, node 4, and its value is 3. So we are at the odd level, so in odd series I'm adding it, in even series I'm subtracting. So 0 plus 3 is 3, 7 minus 3 is 4. So 3 and 4, right? For this node, odd and even series will be 3 and 4. Since I'm at the odd series, so since I am at the odd level, odd series value will be the result of node 4, that is 4. Try calculating it. This is exactly what you will get, right? Now, yeah, odd is 3. My bad. Here it will be 3, right? Because I made a mistake here. This will be 3. I'm at the odd level series. I'm at the odd level. So odd series value will be the result. It should have been 3. I made a typo. My bad, right? This is 3. Now that I have calculated it, I need to go back, because for node 4 there's nothing left to explore, so we'll track back to node 3. So if I'm going back to node 3, the values which are odd and even should be the same which were there at node 3, right? Basically you have to roll back when you are tracking back. That's why I'm saving the values here, right, along the nodes. So if you come back from the DFS call, you must roll it back to the original value, which was 07, right? I'm back to 07. From here, I'll move to node 5. When I'm at node 5, this is again at odd level. So 2 will be added to odd series, 2 will be subtracted from even series, because value of node 5 was 2. So 0 plus 2 is 2, 7 minus 2 is 5. So 2, 5, right? And since I'm at odd level, odd series value will be my result. So if you see from here, this is the max thread value. So if you see what we are doing here, in a single DFS, we are calculating values of each and every node, right? Thread value of each and every node. How? We are utilizing two different series, odd series and even series. Odd series to calculate the result of nodes at odd distances, even series to calculate the result of even distances, right? Even distance nodes. And all we are doing is keeping two different variables that is used to calculate the to apply basically Cadence algorithm to calculate the odd and even series. Just using these, we are calculating the overall result, right? Again, I made a typo. It should have been 3, right? Now, so this is the dry run. Hope you have understood the algorithm. Now let me take you to the code, right? So if you look at the code, okay, here. So see. So there are multiple test cases. So reading T, and in each test case you will be given n and then value of each node that I'm storing in AR. AR is defined as an integer array. LL is long, right? So integer array 2 into 10 power 5, because n at max can be 2 into 10 power 5. This is the result array, and these are two integers to keep the result of odd and even series, right? This is my graph vector of integer. I'm using adjacency list. 2 into 10 power 5 size again. So I'm reading n, saving the value of each node, and also I'm clearing the graph for each node, because there are multiple test cases. So it is possible that in the graph we have the adjacency list of previous test case. So that's why I'm clearing the graph, right? Done with the value and the graph initialization, the graph clearance. Now here I'm initializing. Once you read all of the integer values of each node, you'll be given exactly n-1 nodes. So n-1 for loop for n-1, each time reading the edges and creating a graph, right? Undirected graph. Once we have the graph, you can set odd and for each test case you can set odd and even series to 0 and then start the DFS. I'm starting from node 1 because 1 is the root node, and passing its parent to as -1 because root node doesn't have any parent, right? And then 0 as level. Root node is at 0 level, right? So go back to DFS. If you see here in DFS, I have odd and even series value. I'm saving it, right, in temporary variables. Odd and even some values I'm saving in temporary variables so that I can roll back. If you remember here from node 4, when we track back to node 3, we had to roll back the odd and even values, right? Exactly for that reason I'm saving it, right? So I have odd and even series value, right? If I'm at the odd level, right, if I'm at the odd level, current nodes value will be added in the odd series. Simple. I'm at odd level, so in the odd series I'll add the value, and in the even series I will subtract the value. If the value goes down, I don't take that, I'll take 0. That's why max of 0 or even series minus current node value. As simple as that. If I'm at the even level, what I'll do, in the even, current nodes value will be added. In the even series, current nodes value will be added, and from the odd series it will be subtracted. That's exactly what I'm doing here. And again, I'm making sure that I don't take any negative value. That's why I'm taking max of either 0 or odd minus current node value, right? And once you have calculated the or updated the even odd series, you can set the value of current node. So if we are at odd level, result of current node will be odd series. if we are at even level, result of current node will be even series, as simple as that, right? Once you are done with this, you can go ahead and make DFS call to the children node, right? So I'm going through each child in the adjacency list of current node. If it is not equal to parent, so if you have tree, you have come from node 1 to node 2. In the node 2, you will also have node 1, because this is undirected graph, right? But you don't want to go back up, otherwise you will end up in infinite loop, right? So if current node is not equal to parent, I don't want to go up, only want to go down. If child is not equal to parent, make a DFS call to that node, and of course current node will become will make a DFS call to child, and current node will be its parent, right? Level you will pass as L plus 1, as simple as that. Once we are done with the DFS, we'll be back here, right? When we are back here, I am resetting the odd and even series value, which I had saved earlier. Remember here, when we came back from node 4 to node 3, I reset the value of odd and even. That's exactly what we are doing here. So after the DFS is done, that means you are back here, you just reset the value, so that when you make a next DFS call, when you track back and make the next DFS call, the children have not affected the value of odd and even series, right? As simple as that. So yeah, so this is the DFS. As you can see, in a single DFS, we are calculating thread value of each node using DP, right? Cutting's algorithm, and two different series to keep track of, right? So since we are only applying single DFS, each test case at max runs in linear time, right? DFS runs in V plus E time, where V is the number of nodes and E is the number of edges. Number of nodes, number of edges are n plus n minus 1 and n minus 1. So overall time complexity for T test cases will be T times n, right? We are solving each test case in linear time. So this is how you solve this problem. What was it? Kirei attacks the estate, right? So this is it for this lecture. Thank you for watching. If you have any doubts or any query, anything or any suggestion, you can post it down in the comment section. So again, thank you for watching. Till the next video, keep going.